Okay, I'm going to solve this problem. This is the problem from the quiz. I know we're not supposed to probably copy the quiz, but given the quiz doesn't count towards your final grade, that's what I'm going to do. So I'm going to use the same methodology that he does, which is kind of establishing these two states. Remember that the Bayes probability is going to be used. You've got two variables that you're working at the same time. So let's just use this this same example. So you've got a good state of the world and you've got a bad state of the world against which you have, so that's your condition A. This is your A condition, right? And then your B condition is going to be whether or not people buy, right? So B for buy, A for whatever. Recall from the recharge phone example in class, in the good state of the world, 60% of the customers will actually purchase. So that's in the good state of the world, who purchases, you're going to get 60%. In the bad state of the world, it's only 20%. So 20% of the people are going to buy. It's statistics, so everything is in percentages. And then you consider the good and bad state of the world to be equally likely. So that's 50-50, right? So now you've got your kind of your chart set up. Now let's go look, and now you've got your chart set up. So this is basically your model. This is how you expect it to be. But now you run into reality. So reality, you've got two different people. You've got this person Meg, and you've got Maggie, and you run into them and one of them purchases and the other doesn't. It doesn't matter which one does, which one doesn't. But so what you've now experienced is somebody bought, somebody didn't. Let's go look at all the possible states of what could have happened here, okay? So forget what really happened. We're going to talk about what could have happened. Meg could have bought and Maggie could have bought. Meg could have bought and Maggie could have not bought. Meg could buy and then not buy and then Maggie could buy. Or Maggie might not buy and Meg might not buy and Maggie might not buy. Okay, so that's all your possible states. That's everything that could have happened. Okay, and now you know that 60% probability is a purchase. So you know somebody bought, don't know who it was, but somebody bought. So this is what you were expecting. This is what you got. This is the probables. So you can actually go and you could say, well, look, this is going to be a little bit of jump in the gun, but this is nevertheless how it works. The probability of a purchase was 6 out of 10, right? 60%. So the probability here was 6 out of 10. The probability here 6 out of 10. The probability here was 6 out of 10. The probability over here was actually 4 out of 10 that there was no purchase. Now, the problem here is you had two events at the same time, right? So this is like rolling a dice, right? How does a dice work? 1 out of 6 is going to be whatever face you want, right? But if you want to roll, let's say, 2, you want to roll snake eyes, right? You have a 1/6 probability of the first one and a 1/6 probability of the second one, meaning that your probability of both together is 1/6 times 1/6, right? Right? So your probability here, it's the same thing. You're not using dice this time. You're using this over here. So it's 6/10 times 6/10. So the probability of this happening, given this probability, is 0.36. Okay, so if you can do that over here, you can do it over here. 0.4 times 0.4 is 0.16, right? So now, if you take the 0.36 plus the 0.16, you have 0.52, right? So if you have 0.52, meaning this doesn't work, so you have 0.52 of it doesn't work, that means that you have a 0.48 of it working, okay? So now you know the good state. You've solved for this. You've solved for the probability you thought was going to be 0.6, but it's actually, but now this was your guess. You now came across reality. So in reality, you've experienced 48% of the time you think you're going to get a purchase, okay? And we're going to use that to go inform us about this, right? So, and I'll clean that up in a minute. So now that we know the good state, let's just go calculate, so this is all under good, right? We used the good probability, so that led to the good, right? So now let's go do the bad state of the world. So we end up with the same model, right? Meg can buy, Maggie can buy. We have a yes and a yes and a no, a no and a yes, and a no and a no. But this time, instead of it being 60% probability over here, it's 20%, right? This is the probability. The B is the probability of a purchase. This is the probability of a purchase. So I've got 0.2, I've got 0.2, that means I've got 0.8 here, that means I've got 0.8 here. I don't know what this is, so I'm going to go solve for that. 0.2 times 0.2, I've got 0.04 here, I've got 0.16 here, 0.64. I hate when people make math mistakes like that, so because it screws you up, so I'm sorry about that. But 0.04 plus 0.64 is 0.68. I'll slow down a little bit so I don't screw up as much. So that means that this not working, you're trying to figure out this. That means that this space is 0.32, okay? So now you really have everything to answer this question without using the Bayes theorem, right? So look, you saw a purchase. You saw one purchase, not the other purchase. So you saw this, and you're in the good state. So what's the probability you were in a good state given that you saw somebody purchase? Well, here's the good state plus the bad state. What's the probability I'm in the good state? Well, it's the probability I'm in the good state, right? Divided by the probability of all states, right? This is the whole part divided by the whole. Gives you the thing, so that equals 0.6, 60%. So then that means that what is your posterior probability about given the good state of the world? After you've got all the information and you've plugged and chugged, what is your posterior probability? It's 60%. So the answer is, on this one, it increases to 60%. Okay. Now, what if instead of doing all that, we used the Bayes theorem? So the Bayes theorem, I'm kind of running out of room, so I'm going to slide it up here. So this is if we do the Bayes theorem. So the Bayes theorem is the probability of A given B is equal to the probability of A times the probability of B given A divided by all of the probabilities of B. Okay, just it was helpful for me. Does it matter which order you put these in? Yes. This means what is the probability of A given that you know B? This is the probability of B given that you know A. So this is, from the prior stuff. If we do this, let's do smoking and drinking, right? So, and let's make A be smoking and B be drinking, right? So this is, what is the probability of somebody smoking given that I see them drinking? And then this one over here, which is different, what is the probability of them drinking given that I see them smoking? So they're different ones, and they're going to interact in the same way. You're going to end up with a, kind of a chart that you fill in. So in this case, smoking, yes, smoking, no. And then what is the probability that they drink, right? Just because they're smoking, I don't know, means that there's a 20% probability they're drinking too. I don't know. Versus 0.8. So again, but this is how this works, and this matters, right? So in this example, what is the probability of A? Well, the A state is good. That's what we're trying to figure out. So good for us. We've got the right model. What is the probability of A? And then what is the probability of B given A divided by all the probabilities of B? So in this case, what is the probability of A? This is, you're mixing your guess and your reality. So, but you were guessing it at 0.5, right? And then you're going to multiply it by the B given A, which is this, right? This is B given A, right? So you're going to multiply it by the 0.6. and then you're going to divide that by all of the probabilities of B's. Where's the B, right? We did good and bad, so we're mixing here a little bit, and I don't really like that. But the B is down here. So the probability of all the B's is actually 0.5. So 0.5 times 0.6 is 0.3 divided by 0.5 equals 0.6. It's the same 0.6. So that's how you do those, and so this is just, it makes way more sense for me up here. This is if you use the Bayes theorem, and hopefully that helps.